I'm very happy. I'm very happy to introduce Xuenan Li. So she got her PhD from NYU Courant in 2023 with Bob Cohn, and she is now an assistant professor at Columbia University in the Department of Applied Mathematics and Physics. And she's going to talk to us about the Kagome lattice as a mechanical metamaterial. So please take it away. Thank you.
Thank you. Thank you. It is a great honor to be here to give a talk on my thesis research I did for the past few years. So this is not about data science, but maybe at the later part you will see there's a kind of a similarity between the data science problems and the work I did in the material science. And also, I think people here are not very familiar with what I mentioned as a Kagome lattice and probably the mechanical metamaterial. So let's go through that part first. Okay, so the mechanical metamaterial is still a very giant word. If I spend the introduction on that, it's going to probably take 10 minutes. So let's focus on a very specific part, which is very related to my research. This part is called the mechanism-based mechanical metamaterial. So the most important thing here is a mechanism. So I want to show what do we mean by mechanism. So let's start by thinking about a checkerboard metamaterial. So let's think about you have an elastic sheet, and then you draw the checkerboard pattern there. So you have the black panels and the white panels. So now you bring a scissor and then you cut the white panels out. You cut it in a very specific way so that the black panels are still going to connect to each other. And they're connected in a very thin hinge. So if you rotate the black panels towards each other, it's only going to cost you a small bending energy. Comparing to if you stretch the black panels, it's going to cost you a lot of energy. So, well, I will show you there is a deformation from here to here, which is only going to be about rotating rotating the black panels. So, well, if you can use your imagination, you can see what are that. But let me show you the animation. So originally you have this. And if I play the video, you will see I rotate the black panels and then it's deforming. And you can see there is a global deformation, which is actually here. Okay, you can see it shrinks, right? So, and actually this is the isotropic compression. So if you shrink in this direction by some amount, it's going to shrink by the other direction by the same amount. That's what I mean by isotropic. So, okay. So if we start with this one as my reference state, you can still do compression by compressing the panels, right? It's going to cost you a lot of energy. It's still going to give you some isotropic compression at the end, but comparing to the deformation here, I show you it's going to cost a lot of energy. So this deformation showing in the animation is something what we call a mechanism because it has small energy comparing to the previous one, like just by shrinking the panels. Okay, so this kind of material, you would have a very small energy deformation, which we call a mechanism. Okay, so far so good on defining what I mean by a mechanism. Let's go back to. Okay, so this is the deformation, which is the mechanism. So now the question is, I want to have a material and sorry. Oh, so once I exit the oh. All right. So all right, the problem here is like I still have an elastic sheet and I want to cut the checkerboard, but I cut it in a very small and dense way. So the holes is going to be smaller. And actually we want to take the epsilon, we want to take the holes like epsilon scale. So, and the question here is like, this material is going to be degenerate because you have a deformation here to here, it's like costing you very, very small energy. So this material is like very degenerate. So the question is like, can you still view it as a material if I take the epsilon goes to 0? So because I mean, if I have a mechanism like a low energy state, then you might not sustain some forces. But the question here is like, is it very, very degenerate such that it can sustain no forces, or it's just going to sustain some forces? So some physicists have pointed out they did the research, they have the elastic sheet, and then they cut the small holes. And then you can see when they pull on the left and right and then push on the top and the bottom, you can see if you wash out the small scale, it's kind of behaving like a material. So this is what we call effective behavior. So if you forget, like we still have the small holes, it's kind of like there is a material. It's like something like, well, usually I use the eraser because like an eraser, you can push on the top and the bottom and then pull, it's kind of a material. But here it's like, even though you do a polar structure, it's kind of still like behaving like material. Okay, so, and nobody restrict us from doing square cuts. So Ian Tabasco and his collaborator Paul Klusinski, they did some quadrilateral cuts. So here you have the panel, you have elastic sheet, but then you cut the quadrilateral cuts. So you can still have some kind of mechanism which are low energy deformations from the left to the right. And if you cut them in a different pattern, and the effective behavior would be different. And one type is going to be elliptic. So for example, the top one, which is kind of the square cutting. So that one is actually elliptic. So the deformation from the left, this one, to the deformation. So the deformation from this state to that state is actually governed by elliptic equation. And for a different cut, like this one, so if the deformation in the effective behavior from here to here is going to be a hyperbolic equation. So the design, the cutting is very important. Okay. So nobody restricts us from doing just in-plane deformation. You can also do like out-of-plane deformation. But in this way, you have to design the materials in a more careful way, such that if you put them on the left and right, it will bulge on the to a 3D surface. And you can do some similar things, but this one is do a different cutting. This one is actually the Kagome, a Kagome cutting. And then you can see if you do some special design, it can fit a balloon shape in a very good way. Okay. So let's go back to the Kagome lattice. So this is tiling. Kagome is a tiling. So it's actually combined with equilateral triangles and the hexagons. So now you can tile the entire plane. And again, we want to think this one as a material. So so you have an elastic sheet, and then you cut the white hexagonal holes out. And then the hinges connecting the black triangles are still small enough so that the bending is going to be small. So the rotation is very energy free in this setting. So it's very similar to the rotating square. So it has a deformation from here to here just by changing the angles. I need to, let's see. I want to plot animation. Is that going to cause the problem? Okay, is it still screen sharing?
It is, yeah.
Okay, so let me show you the picture, the animation here, because it's more easy to visualize the animation to see what a mechanism is here. So originally we have this one, and finally you can see the red box is like shrinking, right? Actually, I can tell you this shrinking is also isotropic. So if you shrink on one side by some amount, it's going to shrink by the other side the same amount. Okay. So so this one looks like just the rotating square lattice. It's just a different cutting, but it's still like rotating squares. But the difference between this lattice, the Kagome lattice, and the rotating square lattice is, the next page, you no longer just have one deformation. So you also have some other deformations, which can be deformed to this one or deformed to that one. So if I think I need to point out here, so if you see the cursor here, this hexagon is reappearing here, right? And it's reappearing here. but not the neighbors. So this is different from the pattern I show you here, because here the hexagon is like reappearing in its neighbor and it's reappearing in both directions. So this is what we call one periodic. So the hexagon is like reappearing just by one block. But this one is like a two periodic because this hexagon reappears like 2 blocks away. And we also have some pattern which is like 3 by 1 periodic. So this is like you have a hexagon reappears here by 1 block in the horizontal direction, and you have this one reappears in 3 blocks away in another direction. So we can see that these patterns are not the same one as I show you here, right? And somebody also found, okay, they do the numerical simulations and they find there is a 5 periodic mechanism, which is it's there. I don't know what is the analytic form for that, but it's there. So the difference between the Kagome lattice and the rotating square lattice is you have more mechanisms. You have more degrees of freedom to deform your material by small energy definitions. In the rotating square lattice, you can only have one. Because if you have a square, you want to deform it and you want to preserve the side length, there is only one angle to deform that. You can deform to a rhombus, but only one angle. But for the Kagome lattice, you have more degrees of freedom. So this material, if you cut through the Kagome lattice cutting, then you have more degrees of freedom. Your lattice material is more degenerate.
Would there be more than this? They just haven't been found yet, essentially. Or...
Yes, there are many more. I can show you in the next page. But so the question here is well, can you find all the low energy states? Can you find all the mechanisms? The answer to that is probably no. And another question is that given you have all those kind of mechanisms, are we still able to find what is effective behavior? This is like a very degenerate lattice problem. Can we still find its effective behavior? Is it still meaningful to discuss as epsilon goes to 0, can it still have it's behaving like a material, like a normal material? So the short answer to the previous one is you shouldn't think about enumerating all the mechanisms, because I showed you something like before, you have 1 periodic mechanism, you have 2 periodic mechanism. If you enlarge your unit cell size, and you can have like 5 periodic, 6 periodic, it's just anywhere. And people believe like you can have any kind of periodicity. And another question is like, why are we just focusing on the periodic mechanism? There is a non-periodic mechanism. If I just show you the picture here, you might not believe it. But let me pull up the animation and it will be easier to see. Okay, so this is my reference state. So all the equilateral triangles are there. And what's happening here is some angles change. And you see there is a shrinking, but the deformation state is symmetric to each other in the middle. So this is definitely not periodic. This is something what we call non-periodic state. So this is also a mechanism because all the equilateral triangles remain equilateral triangle and the side length is still the same. So I'm not deforming the panels. So there is like very small energy. Okay, so given that, if we still want to study, okay, so we have a domain, and then we filled in the epsilon scale Kagome lattice. So the triangle side length is going to be epsilon in this case. And we want to study if epsilon goes to 0, is it still meaningful to discuss it as an effective behavior? And to answer that question in a more detailed way, if I set the side length as epsilon, because in normal case, you don't have a material which can take epsilon goes to 0, right? In a normal case, you just have something fixed epsilon, just small. So what are the small deformations on the epsilon scale? And we know for deformations like mechanisms, they're exactly 0 energy, or maybe it's very small energy. So those are the candidates. And what are the other small deformations? I can show you they can be conformal maps.
Look at the Q&A, there's a question online. We have preserved symmetries.
Do we have? What is a preserved symmetry here?
I mean, you sort of, yeah, exactly. You sort of answered the question already, which is there are mechanisms which do not preserve symmetries, right? You can break the translation symmetry of the original structure.
Yes.
So I think that's, I mean, I guess one question would be, are there, is there some subset of mechanisms which always preserves periodicities? Or,
Oh, then the non-periodic one is just a counterexample.
right.
Yeah.
Which is the two things there. I'll clear those.
Okay, I think the most exciting part is like how we get the conformal maps are the small energy states. And that'll be the main topic. So the question is like how we do the models. So instead of thinking about elastic sheets, so we just use spring models. So in this case, we just for a given domain, and then we are going to fill in the Kagome lattice by springs, by the epsilon scale of springs. And then the energy is going to be like the spring energy. So each spring is a Hookean spring. So now we're just going to get the spring energy on each epsilon scale spring. And then we sum it up. But even though for each spring is a linear Hookean spring, once you sum over all the springs in the lattice, it's not going to be linear. So this energy is not quadratic. I think that can be seen here. And so this is a non-convex energy. So there is actually something wrong with that energy. So if I figure out this like a few years earlier, then I wouldn't be troubled into. So the energy I wrote there is not very accurate. It's not very accurate. So what's the problem here? I have a. So I bring those twice just to make things more visualized. So even okay, so we have states of this one and the state of that one. So they both are kind of the zero energy states because they preserve the length of the springs, right? So the energy I showed you before here, it will only see the final state. So if you deform by the U epsilon, then the deformed state here, it preserves the length of the spring. But what's actually happening for this one is the triangle flipped. Okay. It's probably easier to see it with the toy. Sorry. So this is one state on the left. And you can rotate the triangles such that this is one kind of mechanism. But what's happening here is you flip the triangles like this. So triangles flipped is not something we desired in the 2D deformation. Because if you really want to achieve this state, you have to do it in a 3D, right? So if we really want to have a state from here to here in 2D, you have to break the bars. And then you can shrink the size of one bar and then to another, and then it can flip. Sorry, I cannot show you that. So you have to, from this state from the left state to the right state, you have to cross some energy barrier. So that's the point. If there is no energy barrier from this state to that state, it's kind of, I cannot draw my energy landscape in this way. So from this state to that state, I need to cross some barrier. This is like a double well state. But as you can imagine, this energy landscape is not like that because it's very high dimensional and this is a set, not just 2 points. So I want to prefer the state of this one because the state of here is like flipping is not very desirable in the material science literature because you do not want to flip your materials locally. So locally, if you have an elastic sheet and then you do the flipping, it's going to cost you a lot of bending energy. So that's the point. Okay, so to avoid that part, so we just tilt it with some penalty energy. And that penalty energy is determined, so it's depending on the determinant. So once your triangle is flipped, its local determinant is going to be flipping, like from positive to negative. So we want to have some penalty energy just on the determinant. So that's why I have a term here. So I want to have some function and it's evaluating on each equilateral triangle. Once the triangle is flipped, so its determinant is changing, and I would like to have a large penalty. And that penalty is going to be something like order 1 over eta. If eta is like small, it's going to have a huge energy. Okay. And also,
what is eta?
oh, eta is the penalty term. So once the determinant becomes negative, so that means my triangle is flipped, then the W eta evaluated on that triangle is going to be 1 over eta.
Okay.
So and that eta is going to be something here. So this, because I mean, previously I have 2 states, so those are the 0 energy states. Now I want to tilt one, but I don't want to tilt it just by a small number. I want to tilt it by a large number to avoid those flipping actually happens. Okay. So the question here is, now I have defined energy, which is more reasonable, which is more physical. So I want to study the effective behavior. So the energy depends on the epsilon, which is the lattice spacing. And also it depends on eta, which is some kind of penalty term. So I want to study, okay, when eta is small, that's like I have a huge penalty. And I take epsilon goes to 0, that's going to be my effective energy. So, and how we define this convergence by taking epsilon goes to 0, that's going to be some gamma convergence.
What do you choose for W eta? Does it matter what you choose here?
Oh, it has to satisfy just 2 properties. So one property, so the function is going to look like this. So it's going to be a 0 if your determinant is like positive, a large positive, because
So it's a barrier at 0 essentially.
yes, because for this part it's like if my determinant is like approximately 1, that means like I didn't change too much, then I don't want to have a penalty term. Otherwise, my energy is like poisoned. So, but also if the determinant is like becoming negative, I want it to be very, very large. Okay, so
So I'm still a little confused, like, so the U's, they're like 3D vectors.
the U.
Like, I don't really understand how you can possibly get to a sort of flipped orientation.
Oh, the U is here just a 2D deformation. So U epsilon is going to be on x1, y1, xy, and then U is going to be U, xy, v, xy.
So to change the orientation of a triangle, wouldn't you? Isn't that already very expensive?
So maybe this is my reference state. So if I change it to here, then I can still define, maybe here this point is like -1/2, and then maybe square root of 3 divided by 2, and this one is that. Now you flip it, it's going to be reversed.
Okay, I guess you just want ground states, right?
Yes.
So flipping is also a ground state.
Yes,
Yeah,
but that's not
I
a,
remove that.
yes.
Okay, I think I understand. Thanks.
Yeah. So we have the energy, which is depending on the epsilon. And now let's just think about, we fix the eta so that you have a very large penalty term. So we want to study what do we mean by saying like taking epsilon goes to 0. So this is something called gamma convergence. So if we have some energy which is associated with epsilon, okay, so this energy is something related to epsilon. If we say something like as epsilon goes to 0, this energy is gamma converging to this energy, what we mean is the minimizers converge weakly, maybe. So we have this U star epsilon is going to be the low energy state on the epsilon scale. And U star is going to be the low energy state for the effective energy. So what's actually happening, as I mentioned, gamma convergence is actually this minimizer is going to converge to this minimizer. Okay, so that's what I mean by gamma convergence. And if we want to show like conformal maps, are those like the small energy states for this energy, then I just need to show the effective energy is going to vanish on the conformal map. Because if I have this part, the minimum states are going to be conformal maps. Then if there is a small energy states on here, it's going to be approximately a conformal map. Okay, so the key point is like how we show here the U star must be a conformal map. So the first thing is, so if epsilon goes to 0, we need to make sure that the effective energy exists. So that's my energy. And here, this is the part I omit. So using some general tools from calculus ovation, we can say like as epsilon goes to 0, the gamma convergence hold. Okay, so I didn't show you the proof, anything like that, but this can be proved. So as epsilon goes to 0, that energy, this energy, is going to converge to the energy here, gamma converges. And it's in an integral form. You have an integrand which we call the W effective eta. Here I just fix eta. And it's going to be taken on gradient U, because that's a string. And this W effective eta for a given string like lambda is going to be a double minimization. And here I didn't tell you the energy. The energy is some form like that. So I think people here are probably not extremely familiar with this formula. So let me explain a little more about this formula. So what's happening is, just considering if we want to take a grid, so if we want to consider a affine deformation. So let's consider U is a affine deformation. For example, lambda dot x. Okay. So then the question is, how are we going to get the effective energy just for an affine deformation? So then this is going to be W effective eta and then evaluated at lambda. And what is that? So that is going to be a double minimization. This actually means I want to find the smallest energy for some deformation, which is lambda x plus phi, where phi is some periodic functions, but you don't know what is the periodicity. And you find what is the smallest energy you can use for the lambda x plus phi. So the reason why we need to consider all the periodicity is, for example, thinking about the Kagome lattice, you can see some definite for some deformation like isotropic compression, you can achieve that by 1 periodic. You can also achieve by 2 periodic. So something here. So a deformation which can achieve this state, this is a 2 periodic deformation, and this is a 3 periodic deformation. So they might both achieve isotropic compression at the end, but they through different periodicity. So if you want to consider the smallest energy you can achieve for an affine deformation like lambda dot x, you have to consider all the possible lambda x plus phi, where phi can be any kind of periodicity. So for example, if I want to achieve isotropic compression, here you might say I can achieve by 1 periodic deformation. You can also achieve by 2 periodic deformation. They might both achieve by 0. But if you consider some other lambda, which is not isotropic compression, for example, a shear, okay, then you probably locally, you don't want to consider just the shear and plus some 1 periodic oscillation. You can also plus some other oscillation. And okay, and the reason we want to consider that is So the homogenization for the real reason why we consider this, because if you have a deformation which is like lambda x plus phi, okay, so its gradient is going to be lambda plus gradient phi. So if you average out, this part is going to be lambda, right? But this part is going to vanish. So this is the reason why we consider all the lambda x plus phi. Is that okay? So this is some this is some reminiscent theory. So the theory exists for a long time, which is called the nonlinear homogenization. So if I just derive this as a theorem, there's like nobody like the experts is going to be shocked. So what's more shocking here is, can you find some properties of this very funny shaped functional? So people have, like, in many cases, they write the effective energy just like this. Like you have an integral form, and then in the integrand, it's like a double minimization. And people usually just stop there. Like nobody just study what is the property of this W effective eta. So here we want to study, okay, for a given lattice like this, can we study some properties of this W effective eta? Okay.
So I guess you say for a fixed eta positive,
Yes, for
right?
a fixed
So
eta.
is it fair to say that the standard theory breaks if you try to take theorem to try to naively take eta to 0? Is that
For taking eta goes to 0 is okay. But if you want to just study like eta is already infinite, is like already 0, that's going to be problematic.
okay, right, okay.
Yeah, because I mean, restricting all the deformation is going to be a determinant positive is hard.
Okay.
Yeah, the question is like, if you have a deformation which is like a determinant positive everywhere, can you approximate with a affine with a piecewise affine function that achieves also locally determinant positive? That's not known.
Okay. And the eta small, that corresponds to like a really severe barrier. at
Yes,
0? Okay,
yes.
got it. Yeah.
So for this one, we just need some eta like smaller than maybe 1/16, something like that. Yeah. We don't have to take eta like goes to 0.
But I think that does correspond to the physical model, right? Where they
Yes.
can't like switch at all. That would be eta equals 0, or just eta small. Okay.
Yeah, I mean, when eta is like small, you can already like restrict yourself away from studying the because I mean, we draw the penalty, like this is like 1/eta. So, and we also have the energy deformation like this. It's going to cost like extremely just small energy.
Okay.
So having those 1/eta is like another minimum, or maybe a local minimum, but that's something we don't really want to see.
So how does W depends on the eta? This energy function.
Because I mean, the energy I didn't write here is actually some form of this.
But it is a linear term.
It's not a linear term.
It's only, but when epsilon goes to 0, is it like elasticity should become pretty linear, or it could be non-linear?
Which one becomes linear?
Just in general, when you deform the material and when epsilon goes to 0, and the YW eta is still kind of linear.
Oh, the W eta, you mean linear on which part?
With respect to U,
No, it's not.
it's not. Okay.
Because this part is like, W eta is not a linear function. It's something like this.
So what's the meaning of eta again? Sorry, just.
Eta. Okay, so the W eta function is something like this. So when you cross the y-axis, it's going to be evaluated by 1/eta.
Mhm.
Yeah, so if you have something like negative, it's going to be extremely negative. It's going to be small, at least greater than 1/eta. So that's why we can kind of avoid having a negative determinant.
So, yeah, so the physical meaning of eta is what? This term, this eta term, is this
It's the energy on the, so it's the energy once you flip one triangle.
Okay.
Yes. So if eta is like small, then 1 over eta is large, then if you flip one triangle, it's going to cost you huge energy. And the gamma convergence is only going to see at least the global minimum, not just the local minimum.
I see. Yeah, thanks.
You can't guarantee though that you might not just flip one triangle
Yeah,
somewhere because
locally
you
you
have so
might.
many of them, like in a large like macroscopic sense.
Yeah,
You
so
might still flip some triangles as long as
Yeah.
it is positive.
yes, so at the epsilon scale, you might the minimizer might have 1 or 2 or 3, whatever, a small number of triangles flipped. But they might, but overall you would see like that's epsilon square over eta.
And you can't do this with like an actual like barrier function like people use in optimization where
For the barrier.
it actually goes to infinity as the determinant goes to 0.
This is like having some barrier function.
But this thing allows negative numbers, but you could just take it, you could take like eta, you could take W to be 1 over X or something. So that it just goes to infinity as X goes to 0.
Oh, but
And
then,
you like, strictly don't allow anything.
but adding the strict determinant positive is very, very hard. So the same question appears, like if you have a determinant positive, how would you approximate with some piecewise affine function, which is still determinant positive?
So your energy has to be defined sort of for all U's. You can't just restrict it to positive.
Yeah, it's extremely hard. So even in the homogenization side, like if you have a strict restriction on determinant is positive everywhere, it's a very hard problem. Yeah, we can discuss later, but. Okay, so the key point that we think is the most interesting part is that we can show the W effective eta actually vanishes only at isotropic compressions. So the W effective eta is only going to vanish when lambda is going to be a constant times rotation. And the constant must be in a range where 0 to 1. You can include 1, but you cannot approximate 0. So one side is very easy. So if you just have an isotropic compression, you can approximate using either a 1-periodic mechanism or a 2-periodic, whichever you like. And then you can find that energy is going to be 0. Because the W effective eta is written as the minimum energy state you can use to get from lambda x plus v. So the other side is much harder. So if you want to show like W eta effective, it vanishes. It's only vanishing on the constant times rotation. I need a lower bound. Okay. So in other words, I need to mention, so if I have a mechanism which is kind of periodic, it's in the form like lambda x plus v, it must be isotropic compression. And the lower bound here has 2 parts. So one part is for the determinant is positive, and one part is for the determinant is negative. So for the determinant part is negative, this one never vanishes. The lambda 2 and the lambda 1, they are the principal strain. So the lambda here is a matrix. So lambda 1 and lambda 2 are the eigenvalues for lambda transpose lambda square root. So this is how much you stretch your materials, like the largest 2 directions. So if we are on the determinant is negative, then this one never vanishes. So we don't have to worry that this effective functional is going to vanish for the negative determinant part. And for the positive determinant part, it's going to vanish only on lambda 1 is equal to lambda 2, and lambda 1 and lambda 2 are less than or equal to 1. So this part is restricting our materials to be stretched, because once your lambda 1 and lambda 2 are greater than 1, it's going to be stretched. Your material is stretched in some direction. Then it's going to cost you energy. And if your lambda 1 is equal to lambda 2, that's actually telling, so if I want to shrink, they must shrink by the same amount. So together with those two, this one only vanishes on constant times rotation. I think that can be believed, or it's just a linear algebra problem you can perform on yourself. So the key point is, how would we show all the possible K periodic mechanisms must achieve isotropic compression? So that's a very key point for deriving this lower bound. And I put it here because it's something everybody who knows high school geometry, everybody here should know, can understand what I did here. Okay, so the problem here is, how will we show all the K periodic mechanisms must be isotropic compression? Okay, so let me draw. So this is one example. So this is a two periodic mechanism. So from here to here, you can see the hexagon is like reappearing here, reappearing here. This is like two periodic. Okay, so how would we see the deformation gradient? So the deformation gradient can be seen by averaging. Okay, so if we sum over all the blue vectors here, it's still going to be horizontal. And if we sum over all the red vectors, it's going to be the 60-degree direction, right? And if we sum over those and that, you would see the length is like the same. And the angle is like 60 degrees direction, 60 degrees rotation, right? So the affine deformation gradient, if we see from here to here, is going to change the average of the blue vectors to the average of the blue vectors here. So, okay, let me do that again. So first we sum over all the blue vectors here, which is something like horizontal. Here you sum over all the red vectors here, it's going to be 60 direction, in the 60 degree direction. And here, if you sum over all the blue vectors here, you can see it's kind of still like in the horizontal direction. And if you sum over all the red vectors, you don't, at this moment, you don't know it's going to be on the 60 degree directions. And I can show you that's going to be 60 degree directions. Okay, so why is that? So the affine deformation from here to here would change the sum over all the blue vectors to the sum of the blue vectors here. And it's going to change the sum of the red vectors to the sum of the red vectors here. Okay, and so let's write. And so here is a mechanism. So the triangles is still going to remain an equilateral triangle. So for each triangle here, the red vector is going to be a 60 degree rotation of the blue vector, right? So if you sum over all the blue ones here, and you sum over all the red ones here, it's going to be 60 degrees rotation. So because on each triangle, you would have the red vector is going to be a 60 degree rotation of the blue ones. So after you sum over all the blue ones and sum over all the red ones, the 60 degree rotation is going to be preserved. Okay, so after the deformation from here to here, you can see the sum of the vectors in the one direction and in the other direction is going to be preserved by those 60 degree rotation. And this deformation can only be constant times rotation. So this is like you have some affine deformation lambda, and it must commute with the 60 degrees rotation. And this is only possible when you have lambda is a constant times rotation matrix. Okay. So far, so good. So this is how we show, okay, so if you have a K-periodic mechanism, it must be a isotropic compression. It cannot be a shear. It cannot be something else. So with that, if you want to have the effective energy vanishes, it must have the gradient is equal to constant times rotation locally, but they can depend on the location where you're at. It might not be a constant times rotation all the way, which is the same. So this one is actually a Cauchy-Riemann equation. Because I mean, what is constant times rotation? It's just cosine, c multiplied cosine, and then negative c multiplied sine, and then c sine, and then c cosine. So you can see the diagonal is the same to each other, and then the other off diagonal is going to be negative. So that's actually a Cauchy-Riemann equation. So if you really have the gradient u is equal to constant times rotation, it must indicate your u is a conformal map. So what I mean is like if u is going to be u1 and u2, those are the two components. And then if you have the u1 plus iu2 is going to be a conformal map. So that's how we show the conformal maps are going to be the small energy states for the Kagome lattice. Okay. So now we know for the epsilon scale Kagome lattice, the low energy state must approximately be some conformal map. Then the real question is, what are those energies? So for a conformal map, how well can you approximate that? So we know there are some conformal maps can be approximated with some O epsilon square energy. So this is one example. So this is one example I can construct that costs me O epsilon square energy. And I can construct another one, which is also cost me like O epsilon square energy, but it's a different structure. But these are just some deformations we constructed. We still don't know what is the lowest energy possible. That is still an open question. Okay. Now we can move to some simulations. So far we just derive what is the effective behavior, like on the macroscopic side. So if we really want to build a material and then we see how we deform it and how it actually deforms, then we can only ask for the numerics for help. So here is like we have elastic sheet and then we really cut the holes, but we do it in the numerical way. And if we compress the top and the bottom and left and right, it's going to deform like isotropically like this, which is kind of like a one periodic mechanism. But if we constrain the boundary, which is like a affine deformation, you no longer see the deformations I showed you before. So this is something numerics found. And this is something I constructed. They're not exactly the same. They are very, very different. So I can show you the video of that one. And it's very, very interesting to see. So originally, you have a panel and then it's cutting like the hexagon holes. And then you slowly push the boundary to a conformal map. And you can see it's deforming like that.
Sorry, so that's the final picture is like the min of the energy for a fixed boundary.
Yes,
okay.
But not exactly the global min. It's probably some local. Whereas we perform the numerical scheme is just something like gradient descent.
Oh, I see.
So it's going to be a local minimum and it's something like this. It's still some small energy like O epsilon squared. But this is definitely a different structure than I just showed you before where I constructed like manually.
So when they solve it, are they doing it sort of bit by bit, like change it a little bit and find the lowest energy and then change it a bit more and solve?
Yes. So they push it every time by a small amount and then they run they run it.
Okay. Whereas if you were to just try to solve it directly on this shape, it wouldn't work or something.
Yeah, it wouldn't work. It would work.
We get stuck in a bad local.
Yeah, because it's very ill conditioned, this problem.
They're only pushing from the boundary.
Yeah, they are only pushing from the boundary. So what's actually happening is like you have this domain, and then you push a little amount on the boundary to the conformal map.
And you get something different every time you run this essentially, or?
Yes.
Is it always epsilon squared?
For most of the time we see is epsilon square. So, and here is like, so what's happening here is like, this is approximating the elastic sheet. So the triangles, once you rotate, you would have some bending energy. Because for a normal material, once you connect them, you rotate, it's going to cost you bending energy. So here we add that bending energy in, it's just adding it to a very, very small constant, comparing to stretching the bonds.
And like the form of that bending energy is like no, or how do you find the form of that energy?
The bending energy?
Yeah.
Or
is that just like part of the original formulation?
Oh, it's not in the original formulation. Yeah, so if we add the energy, it's kind of like once you rotate the angle, originally it's like 120 degrees because those are two equilateral triangles. The angle is like 120. So if you change the angle, we just maybe to 60 degrees, we just add some constant multiply 60.
Okay, so
Yeah.
linear.
Yeah. But we choose that constant to be extremely small comparing to the spring energy we put it here.
Okay.
Yeah.
And then not like, sorry, so many questions. Like
No, no, no,
that mean like changing the form of that would probably change
the
what you
minimum.
get at it. Yeah. Or does
Yes.
it not change the epsilon squared still?
If we make the bending energy like extremely small, it's still going to be epsilon square. But if we turn on that bending energy, then the global minimum is not actually this. At least from what I run, it's actually this. This kind of bow tie structure. And I didn't test what is the energy for that because it's not very reasonable because I have bending and I have spring constant as well.
Okay.
Yeah.
This
So
is,
it's just-
this is with the W eta penalty,
This is also with double eta penalty.
and is it, like, when you change eta, is it?
So when I
changing?
change the eta, it wouldn't affect here because locally I didn't change any kind of
Yeah, so are any of these triangles flipped? I guess they're not.
no, here, not this one, but this one. This one, none of those triangles are flipped. Because I mean, when you see the video here,
You can kind of see it as you watch it.
yeah, no triangles is flipped.
And what's the color mean on the triangles?
Oh, so if it is blue and if it is red, it's kind of like you're rotating clockwise or counterclockwise. Because for the triangle, you can rotate this way or rotate that way. It's going to be symmetric to each other. Yeah. So if you see here, it's like this part and that part is kind of symmetric to each other.
And you said that so the conformal maps come out from analyzing the effective continuum energy,
Yes.
right? So, okay.
Yes, so the conformal maps are the zero energy states for the effective energy. But we can see because of the gamma convergence, then the minimum for the epsilon scale is also going to approximate that conformal
Right.
map. Yeah, but we don't know what is exactly the energy for the conformal map on the epsilon scale. So these are examples like it's O epsilon square, but it might be also O epsilon cube, fourth. Some people claim it's like 0, but I haven't seen the paper out. So it's still an open question.
We just have a couple of minutes left.
Yeah, sure. At least I can finish the part, finish this part. And you can also run some simulations.
Oh, there's a question, sorry, in the Q&A box. My laptop died.
Can you theoretically describe the networks that are forming? What is a network here?
He might just mean the shapes of the structure you're seeing.
In your simulation. It's a spring network. So everything is like connected by spring. So the triangles is going to be connected by 3 springs. It's just like my original model, but I also add a little bending spring. Does that answer your question? Or do you have different types of domains?
So, yeah, like maybe there's some yeah, you could describe the domains that are forming. The red and the blue domains, right? Maybe.
But I mean, those are just the local deformations you can achieve, but because locally you want to achieve some like constant times rotation, it's just this one choose to rotate clockwise, this one choose to rotate counterclockwise. But theoretically defining how we have some brains like this, I don't know. This is not something like I can theoretically describe at this moment. Does that answer the question here? Okay. So I think we can also run some other simulations where we make some boundaries like free to go. So here we make the left and the right boundaries free to change to whatever they like. And then we just push on the top and the bottom. So we can see some symmetric deformation. And if we make it on the sphere, on the disk, it's also something like that. And what's funny is like this deformation must also be a conformal, but here we don't know what exactly this form is. So as an ending here, so the Kagome lattice is very, very floppy. So it can deform in whatever mechanism you can choose, but it's still very meaningful. It still has a effective behavior, which only vanishes on compressive conformal maps. If you give it a shear, it's still going to be some material-like behavior. And some people prefer to approximate this conformal map energy using gradient square minus 2 determined gradient. This one vanishes only on conformal maps. And what's more interesting is that this is only correct on the macroscopic scale. If you zoom in to the microscopic scale, you have a lot more choices. So even though you can conformal, we know the conformal maps are going to be the small energy states, there are many of them. So one choice is this, one choice is this, and there are some others from the numerical simulation. So if we really think about the epsilon scale energy landscape, it's going to be very flat around the conformal map, but it's going to be a lot of local bounds. So this energy landscape is very wrecked, and the interesting thing is like, what is the global minimum? We don't know. We know it's approximating conformal map, but we don't know what is the global minimum and what is the energy for the global minimum. So there are still a lot of things can be discussed. Okay, I don't think I have time to talk about the other things.
Okay, well, thank you for the time.
Other questions from the audience or on Zoom? We just ask a quick question about these final simulations. Like at first, like the one you showed at first, like a few slides ago, it seemed like the blue and red regions were kind of larger. They had sort of some more macroscopic structure, right? There was a large blue region and a large red one or something.
Oh, here and here.
And then the ones you showed later, it looked like it was almost every other triangle was blue or red or something, right?
Oh, you mean, but here is still like.
That one is still, but there was wasn't there another one that's?
Oh, this one is because you have the two periodic forming here.
Okay.
Because I mean, this part here is like you have some two periodic. So this one is kind of mainly just two periodic.
And so then the other ones, right?
This one is like forming mainly by one
Yeah, so then the
periodic.
question is like at some sort of larger scale, is there some understanding of sort of how large these regions are where there's like a consistent rotation angle? Like this should be forming on some larger scale or something, right? And
Oh, you mean on the larger scale? Then,
like if you were to zoom out, you would see these pockets of red and blue.
then I think we need to go to we need to add some, probably on the next level. Like, so the conformal map is like the zero energy state at the first order, maybe going to the next order. But the problem here is like the conformal map, we don't know what is exactly the smallest energy for a conformal map. Because I mean, I think modica motella, that's something like you can define where this part and that part is. But here, modica motella, you need to know what is the smallest energy and then you divide through that. Here, we don't know the smallest energy, so modica motella type of thing cannot be performed.
Any other questions? Okay, thanks for the talk.
So it's different kinds of problems where you have two local